Electronic nose, Wikipedia audio. An electronic nose is a device intended to detect odors or flavors. Over the last decade, electronic sensing or e-sensing technologies have undergone important developments from a technical and commercial point of view. The expression electronic sensing refers to the capability of reproducing human senses using sensor arrays and pattern recognition systems. Since 1982, research has been conducted to develop technologies, commonly referred to as electronic noses, that could detect and recognize odors and flavors. The stages of the recognition process are similar to human olfaction and are performed for identification, comparison, quantification, and other applications, including data storage and retrieval. However, hedonic evaluation is a specificity of the human nose given that it is related to subjective opinions. These devices have undergone much development and are now used to fulfill industrial needs. In all industries, odor assessment is usually performed by human sensory analysis, by chemosensors, or by gas chromatography. The latter technique gives information about volatile organic compounds, but the correlation between analytical results and actual odor perception is not direct due to potential interactions between several odorous components. Other techniques to analyze odors. In the wasp hound odor detector, the mechanical element is a video camera and the biological element is 5 parasitic wasps who have been conditioned to swarm in response to the presence of a specific chemical. Scientist Alexander Graham Bell popularized the notion that it was difficult to measure a smell, and in 1914 said the following: "Metal oxide semiconductor devices, a transistor used for amplifying or switching electronic signals. This works on the principle that molecules entering the sensor area will be charged either positively or negatively, which should have a direct effect on the electric field inside the MOSFET. Thus, introducing each additional charged particle will directly affect the transistor in a unique way, producing a change in the MOSFET signal that can then be interpreted by pattern recognition computer systems. So essentially each detectable molecule will have its own unique signal for a computer system to interpret. Conducting polymers, organic polymers that conduct electricity, polymer composites, similar in use to conducting polymers but formulated of non-conducting polymers with the addition of conducting materials such as carbon black, quartz crystal microbalance, a way of measuring mass per unit area by measuring the change in frequency of a quartz crystal resonator. This can be stored in a database and used for future reference. Surface acoustic wave, a class of microelectromechanical systems which rely on the modulation of surface acoustic waves to sense a physical phenomenon. Did you ever measure a smell? Can you tell whether one smell is just twice strong as another? Can you measure the difference between two kinds of smell and another? It is very obvious that we have very many different kinds of smells, all the way from the odor of violets and roses up to asafoetida. But until you can measure their likeness and differences, you can have no science of odor. If you are ambitious to find a new science, measure a smell. In the decades since Bell made this observation, no such science of odor materialized, and it was not until the 1950s and beyond that any real progress was made. The electronic nose was developed in order to mimic human olfaction that functions as a non-separative mechanism, i.e. an odor/flavor is perceived as a global fingerprint. Essentially the instrument consists of headspace sampling, sensor array, and pattern recognition modules, to generate signal pattern that are used for characterizing odors. Electronic noses include 3 major parts: a sample delivery system, a detection system, a computing system. The sample delivery system enables the generation of the headspace of a sample, which is the fraction analyzed. The system then injects this headspace into the detection system of the electronic nose. The sample delivery system is essential to guarantee constant operating conditions. The detection system, which consists of a sensor set, is the reactive part of the instrument. When in contact with volatile compounds, the sensors react, which means they experience a change of electrical properties. In most electronic noses, each sensor is sensitive to all volatile molecules but each in their specific way. However, in bioelectronic noses, receptor proteins which respond to specific odor molecules are used. Most electronic noses use sensor arrays that react to volatile compounds on contact. The adsorption of volatile compounds on the sensor surface causes a physical change of the sensor. A specific response is recorded by the electronic interface, transforming the signal into a digital value. Recorded data are then computed based on statistical models. History. Bioelectronic noses use olfactory receptors, proteins cloned from biological organisms, e.g. humans, that bind to specific odor molecules. One group has developed a bioelectronic nose that mimics the signaling systems used by the human nose to perceive odors at a very high sensitivity, femtomolar concentrations. The more commonly used sensors for electronic noses include: some devices combine multiple sensor types in a single device, for example polymer-coated QCMs. The independent information leads to vastly more sensitive and efficient devices. In recent years, other types of electronic noses have been developed that utilize mass spectrometry or ultrafast gas chromatography as a detection system. The computing system works to combine the responses of all of the sensors, which represents the input for the data treatment. This part of the instrument performs global fingerprint analysis and provides results and representations that can be easily interpreted. Moreover, the electronic nose results can be correlated to those obtained from other techniques. Many of the data interpretation systems are used for the analysis of results. These systems include artificial neural network, fuzzy logic, pattern recognition modules, etc. As a first step, an electronic nose needs to be trained with qualified samples so as to build a database of reference. Then the instrument can recognize new samples by comparing a volatile compound's fingerprint to those contained in its database. Thus they can perform qualitative or quantitative analysis. This, however, may also provide a problem as many odors are made up of multiple different molecules, which may be wrongly interpreted by the device as it will register them as different compounds, resulting in incorrect or inaccurate results depending on the primary function of a nose. Electronic nose instruments are used by research and development laboratories, quality control laboratories and process and production departments for various purposes. Working principle: performing an analysis. Various application notes describe analysis in areas such as flavor and fragrance, food and beverage, packaging, pharmaceutical, cosmetic and perfumes, and chemical companies. More recently, they can also address public concerns in terms of olfactive nuisance monitoring with networks of on-field devices. Since emission rates on a site can be extremely variable for some sources, the electronic nose can provide a tool to track fluctuations and trends and assess the situation in real time. It improves understanding of critical sources, leading to proactive odor management. Real-time modeling will present the current situation, allowing the operator to understand which periods and conditions are putting the facility at risk. Also, existing commercial systems can be programmed to have active alerts based on set points to initiate appropriate actions. Applications in quality control laboratories, in process and production departments. Possible and future applications in the fields of health and security. Possible and future applications in the field of crime prevention and security. The Cyra-Nose 320 is a handheld electronic nose developed by Cyra-Nose Sciences of Pasadena, California in 2000. Cyra-Nose Sciences was founded in 1997, 9 years after the concept of an electronic nose based on using multiple semi-selective sensors combined with electronic computation was first proposed by Gardner and Bartlett. The Cyra-Nose 320 is based on sensor research performed by Professor Nathan Lewis of the California Institute of Technology. Applications researched using the Cyra-Nose 320 include the detection of COPD, and other medical conditions as well as industrial applications generally related to quality control or contamination detection. In environmental monitoring. Example: